Hello.
Yes, you are audible.
Okay, okay, thanks. So I hope my screen is also visible. Okay, so let's start with today's topic of greedy algorithms. Okay, so does anyone have any idea about what greedy algorithms are, or like have read about them previously? Can anyone raise their hands if they're familiar with the concept? Okay, so most of you are not. Okay, anyway, so greedy algorithms is a way of approaching a problem which basically which is not applicable to all problems in general, but in some problems we can actually have some observations slash some greedy choices we can make such that we get an optimal value. Okay, so that might not be the best explanation, but we will uh, get to know about what greedy algorithms are better when we start some examples. Okay, so mostly greedy algorithms have to do with make a problem simple. So I'll just uh, explain with a very easy example. So if you have, let's say, n numbers, uh, AI, and you want to pick up three indices, so AI as in A1, A2, AN, and you want to pick three indices I, J, and K, such that I is less than J is less than K. So N has to be greater than equal to 3, I guess. Such that AI plus AJ plus AK is minimum. Is minimum. So this is a very easy problem. So can someone just quickly tell me how this problem has to be done?
We simply take the minimum among these n numbers, three minimum
Exactly.
numbers.
Exactly. So you take the minimum, the second minimum, and the third minimum. But someone might want to enumerate all sets of three elements such that they make a pair, they make a triplet, and then compare the sums of all those triplets and find whichever is minimum. So that will be an order n cubed solution, right? So you find for all k, you find a particular j, and for all such k comma j, you find a particular I, and then you check what the value of this sum is, and then for all such possible I comma j comma k, you find the minimum. But here you are making this observation that okay, so if I can somehow choose the three most minimum elements, then I'm done. So this thing I'm doing, this is called a greedy choice. So I'm greedily choosing. Okay, so I'll just put this in quotes. The three minimum elements. And this choice of the minimum elements makes the problem much more simpler than uh, what one would uh, get when they would just enumerate all subsets of three. Right. So this not only makes our problem simple, this actually reduces the complexity from order n cubed to order n. But okay, so this is a very naive example, but I just wanted to get the idea of what a greedy choice or a greedy algorithm is. Okay, so moving on. So in this particular problem, it's like one step is to come up with a greedy choice, and the second step is actually proving that this particular choice of the 3 minimum elements will actually give you a subset which is a minimum. So you can easily prove that arguing something like, okay, so if AI, AJ, AK are the 3 minimum elements, and the optimal solution is AI prime plus AJ prime plus AK prime, then if these 3 elements are the 3 minimum elements of the array A, and if these 3 elements are not the 3 minimum elements of the array A, then there has to be some index, let's say this particular index AJ, which AJ prime, which is greater than or equal to maximum of AI AJ AK. Or in particular, J prime does not belong to the set IJK. But then if you replace this AJ prime with uh, some other one of these numbers, so let's say if you replace this number with AJ, due to this condition, this will give you a better value. So this is the way you prove that a solution, a greedy choice, is actually giving you a correct answer. Okay, more about the proof later on, but this is the main concept that we will be using throughout today's discussion. So any questions up to now? Okay. So as I said, greedy algorithms are best understood with examples. So let's start with some concrete problems that we have. Okay, so this is a problem that is taken from the last year's CDC round, the CDC series round. So the problem is such that you are given an array A, A1, A2, An of n integers, where n is less than equal to 10 to the 5, and AI is something like this, I believe. So basically, the thing is, AIs are large. Now you need to minimize, you need to find two indices I and j such that I is not equal to j, or more specifically, I is less than j, you can say. So aj minus ai divided by j minus I. This value is minimum among all possible pairs ij. So is the problem clear? Okay, I hope so. Okay. So first of all, can someone tell me what is the brute force solution to this problem? So what is the first thing that comes to mind? So what is the first solution that comes to mind? Anyone?
We can just choose I and J independently, and examine for each AI and AJ pair possible, and then find the minimum among them, and that will be the big of n square solution.
Correct. So big of n square is check all pairs. However, as you might have noticed, that big of n square is too large a limit to pass for n less than or equal to 10 to the 5. Now, an observation that we can make is, well, does anyone have some feeling seeing this formula? So, has anyone seen this formula before or something like this before? Okay, so what if I just made it something like,
Can we sort it and just check the consecutive pairs?
okay, why sort it? So how would you get this values j and I when you sort it? So
Oh, okay, yeah.
so you understand the problem. So you lose track of the indices. Okay, okay, like sorting is a good greedy choice that you can come up with. Sorting may not work in this particular case.
We can maybe use a vector of pair and then sort it, and uh, then we can check
Okay.
whether the indices are in that range. We can just that can be done in big O of n.
And log n. Okay. Oh, so suggestion one is what you do, you keep the track of, so you are sorting this pairs, right? AI comma something like this, right?
Yeah,
Okay, so you are sorting these such that you have this information regarding I, and you are checking consecutive pairs, right? Okay, so this is, yes, this is something that you can call a greedy choice, but uh, the second thing that I discussed is you have to come up with a proof for this greedy choice to work. So I'll just write what the suggestion is. Sort according to I, comma I. Check the okay, so now our task is to either come up with the proof or come up with a counterexample. Okay, so can anyone come up with a proof that this thing would always work and this thing would always give you the minimum possible value of this? Anyone?
Oh, hello.
Yes, yes.
Yeah, so I think like aj minus ai by j minus I can be represented as a slope of a line. So once we
Okay.
sort these pairs,
Okay.
then the minimum slope will be obtained between two consecutive pairs.
After sorting.
Yeah.
Okay. Okay. And why do you think so? Or like, do you have proof?
We needed to find the minimum value, right?
Yes, yes.
So if we are sorting uh, according to the values of AI,
Okay.
oh no. So AI was negative as well, right? It was not only positive.
Yeah, that can be taken care of, right? If you want to have AI to be positive, then you can just add 10 to the power 9 or 2 into 10 to the power 9 to every integer, and you will get a positive, and this difference will remain the same. And that's
Yeah,
not an
yeah.
issue. But yeah, so do you have a proof of that?
Or just a minute, I'll think again.
Okay, so can anyone come up with a proof or counterexample for this?
Like, because j minus I can be independent of a I minus aj, so we can't say that this will give minimum. It's not necessary. Because j minus I for consecutive pairs, the j minus I will not be same. If it had been same, then we could have said that the minimum difference would give the minimum.
Okay, okay, but yeah, like maybe this will give you the correct answer. But if you have some doubt that this won't be giving you the correct answer, the easiest thing to do is come up with a counterexample. Or there is a chance that this is actually correct, even if it seems that this is not correct. Okay. So I think the thing is, this is not the intended solution that we had to this problem, but this may also give a correct answer. So yeah, I think we will need to think about this approach later. So I'll just discuss.
Why should we check for consecutive pairs? Because we need to minimize AJ minus AI as well. So we should just, assign AJ to the minimum possible value of the in the array and AI to the maximum possible value in the array. Then maybe some solution. The solution may be correct. Why should we check for consecutive?
Okay, suggestion 2 is I is such that J is such that AJ is maximum, and
So
I
AJ
is
should
such.
be minimum.
Okay, minimum. And I is such that AI is maximum. So first of all, this condition might not hold true, right? For the things that you are saying. So the maximum element, so J was supposed to minimum. Yeah. So the minimum element can definitely come before the maximum element.
Yes.
But
Right.
even if this is the case, I think you might have some counter examples. I'll just tell you. So if you have something like equal to something like 1, 4, 5, let's keep it 1, 5, 6. Okay, well, you wanted the minimum, so the minimum, even if the minimum is occurring after the maximum, so here your minimum slope is you're assigning this to J and this to I, right?
Yeah.
Oh, never mind. The opposite, right? Sorry.
Yeah, I understand. It will not hold.
Yeah, so these two pairs are giving a better answer, I guess. So yeah, this is a valid greedy choice, but unfortunately, this is not correct. So I hope you are getting the intuition behind what a greedy choice is. Okay. Any other suggestions for greedy choices, or any updates on this one? Okay, let's just have some random pairs and see random arrays and see if this is giving us correct. So let's just take A is equal to something like 7, 6, 8, 1 or something like this. Okay, so clearly this to give you the minimum slope, right? Minimum value.
Is the array A an increasing array?
Sorry?
Is the array A is an increasing array?
I'm sorry, I couldn't get you. Could you please repeat?
Is the given array A an increasing array?
No. That's so these elements can be in any. Okay, so when you sort it with respect to ai comma I, so this is, let's just keep it one index to this 1, 2, 3, 4. So you get 1 comma 4, 6 comma 2, 7 comma 1, 8 comma 3. So do any of these consecutive pairs give you a better answer than this? This gives you -7, right? Just check if any of these give you -7. I don't think any of these will give it. So this gives minus, wait, this gives, so it's these two. This is -1, I guess. These two, I guess, is minus half, right? Or plus half. Sorry. Okay. Yeah, so I think we got a counterexample. So this particular pair gives you -7. This gives you +1, plus half, and this gives you -1. So no consecutive pairs in the sorted array would work. Is that clear, or do you have any problems regarding this? Anyone? Hello, I'll be assuming that I'm audible. Okay, is this last part not
Yeah.
clear regarding the counterexample? Let me just check this array. I think this won't work. So if you sort it according to ai comma I and then check consecutive pairs. Okay, so I guess we'll be moving on. So okay, I'll be revealing the actual solution. So this suggestion 1 is very close to the actual solution. So the thing is, you don't sort it and just check consecutive pairs. That's it. Okay, I think someone was saying something regarding this value can be viewed as a slope of a line. So can you please elaborate it once again?
Yeah, like I was thinking further on this. I have not reached any conclusion, so
Yeah, okay.
can
So
you give
like
2 minutes to think?
no, I'm just asking that like how do you visualize this as a line? The slope of a line. So what
Yeah,
are
so
your
the x coordinate should be I and the y coordinate ai. So aj minus ai by j minus I would be the slope.
okay. So this should be your this. So here you have I. Here you have I, and here you have A. So over here you have something like 1 comma A1 1. So 2 will be somewhere over here. 2 comma A2. And well, I and J are somewhere over here. Yeah, yeah, yeah. So you need this slope to be minimum, right? Okay, so does anyone want to think further why this consecutive thing would work, or like should I reveal the proof? So the suggestion is to check consecutive pairs. Anyone? How can you proceed further in the proof? Okay. So I assume that everyone's fine with me revealing the proof. Okay.
Oh, I think let's say we draw a line passing through 1 comma a1 and 2 comma a2.
Okay.
So if 3 comma a3 lies below this line, then 2 comma a2 and 3 comma a3 would form a line of minimum slope than this line.
So what line would you like to draw?
2
Just call
comma
this
a2.
PQR, I guess then.
Okay, so now we draw the line QR.
QR.
So if 3 comma a3 lies below the line PQ, then QR would be a better answer than PQ.
Okay.
And if it lies above PQ. If 3, A3 lies above PQ,
Okay.
then it would not be a better answer. Like PQ would be a better answer than QR.
Okay, that is totally true. But what we are trying to prove here is a bit different than like, so what we are trying to prove over here is that if I comma j give you the optimal answer, then there must be a pair such that ai and aj are consecutive. That is j equal to I plus 1.
Yeah, so we can see here, right? PR would also not be a better solution than QR.
Oh, okay, so you are comparing PR and PQQR, right?
Yeah,
Okay,
PR,
yeah.
PQ with QR. So PR would also will have a larger slope than QR.
Right.
And also,
yeah.
if 3, A3 lies above that line, then PR would have a greater slope.
Correct. That's absolutely correct. So basically, what he's trying to prove is when you, so for the sake of contradiction, assume that there is some other point that lies between somewhere over here. So if this point lies somewhere, so just consider point number j minus 1. So ai j minus 1. So aj minus 1, this point. If this point lies below this line, then this pink line would give you a better slope, slope with a less value compared to the green line, right? So which is a contradiction. Again, if this point were to stay higher than this line, then this white line would give you a better answer. And if this particular point was exactly on this line, then, well, you won't improve the answer, but your fact that there is at least one pair of consecutive integers, consecutive array elements that have the minimum slope still holds true. So even if this value is the minimum, you have some other pair j minus 1 comma j such that these two indices are consecutive and the slope for these two values are minimum. Okay, so that completes the entire proof. So is everyone okay with this proof? Any questions? Okay, I'll be assuming everyone understood the proof. Okay, so I'll move on to the next problem. Well, let's just make a comment regarding this problem. So over here, you see that the proof that we did is a crucial part of the solution. Otherwise, without proof, some promising ideas like you may code up some promising ideas only to find out that these don't pass the test, or these don't produce the correct answer. Okay, so that was the comment I was intending to make. Okay, now let's move on to this question. Okay, so this is the question range partition from a very recent contest by Google. So it's from the Google Kickstart round C. So basically, over here you are given the integers 1, 2, 3 to n, and then you are asked if you can partition this integers from 1 to n into two parts. So let's say in one part you have 1, 2, 5, 6, and in the other parts you have the other integers, such that the ratio of these are x is to y. So you are given with n x y, provided that x comma y have a GCD of 1. That is x and y are co-prime, which basically means that you cannot reduce this fraction further. Okay, so the question is, can you partition this into two parts? If yes, then you need to show a partition that does this. Okay, so is the question clear? So can this be partitioned?
Is the sum of the first partition, right? Sum of the numbers in the first partition, right?
Not exactly. The sum of the partitions of the first partition is to the sum of the partition of the second partition is x is to y.
Okay.
Partitioned into two parts.
So in that case, we can just take x equal to 1 and the rest equal to y. And that should
No,
do
no,
it.
x and y are given. They are given as input. Okay, so I think the problem is
Okay.
not very clear. So can this be partitioned into two parts? Such that the ratio of sum of the two parts are x is to y for given n x y. If yes, so valid.
The ratio of the sum of first part to that second part is x is to y.
Exactly. So, for example, the samples of this problem were something like 3, 1, 2. So n equal to 3, x equal to 1, y equal to 2, and the partition.
So we can first find out the total sum, then just find out if x by x plus into n we can get from the array.
Okay, yeah, that's correct.
X into n, just sum by x plus.
Okay, yeah. So basically, so I'll just complete the sample to this. So basically, you need to partition this array 1, 2, 3 into two parts such that they have a sum 1:2, and over here you can come up with this construction, I guess, 2, 1, 3, right? So the sum of all elements in this partition is to the sum of all elements in this partition is equal to 1:2. So the problem is clear, right? Is there anyone having any doubts regarding this problem? Okay. Okay, yes. So what was the suggestion? So someone was suggesting something like checking whether x plus y or something like that. Can you please repeat?
We can first find out the total sum of the array.
That is
Uh,
n into n plus 1 by 2, right?
yeah. No,
Okay.
means how it can be n into n plus, like the sum of the elements of all the elements. Okay, it's given 1 to n.
Yes. This is not any arbitrary arrangement. This is 1 to n.
Okay, then we can directly find out n. Now we can just find out if the array, the subpart of the array gives x into this sum by x plus y.
Okay, so what is your criteria for giving no?
Like x is to y is the total, like the total sum is x plus y, no? X into k plus y into k.
Okay. So if you call the partition 1 to have a sum of x times k and the second partition to have sum of y times k, then this should be equal to x plus y times k, right?
Yes.
That's your selection. Okay. So what's your condition to say no, you cannot have a partition like this?
If we can't find like it should be divided into two parts. So if using a loop, we can just start finding the sum from zeroth index. Now, if we don't get exact sum as either of xk or yk, then we can just say that it is not possible. Is it correct?
Okay. So can you just explain what are you doing from the 0th index? So are you taking sums like 1, 1, 2, 1, 2, 3, something like that?
Yeah, 1 plus 2 plus 3 plus 4, so on. If we get xk or yk, then it satisfies. The remaining sum will be the other part.
K should be an integer, right?
Exactly.
So n into n plus 1 modulo 2 if it is if n into n plus 1 upon 2 modulo x plus y, if it is not 0, then it is not partitionable.
Okay.
Partition is not possible.
That is very correct. So if x plus y does not divide n into n plus 1 by 2, then you should simply output it. Okay. Now the deeper question: if x plus y is indeed a factor of this thing, then is it always yes, or is it sometimes yes, sometimes no? Depends on something else. Okay, so someone else was saying something regarding seeing from 0th index.
Like if finding the sum that xk on going on, if we just get the sum as xk or yk, then we can say that
Okay. Okay, so you know the value of k, right? So you know
yeah,
x, you know y, you know n, so you know n, you know x, you know y, so you can get something like k equal to n into n plus 1 by 2 into x plus y, right? Okay. However, can you just dry run your algorithm on this particular thing and check? So over here, you'll check that you'll see that k is equal to 2, right? So 3 into 3 plus 1 is 4, by 2 is, 3 into 3 plus 1 is 4, which multiplied with 3 is 12, by 2 is 6, divided by x plus y, 3 is 2, yes. So yes, how are you checking?
no, it's not giving correct.
Yeah, so that is something that might not work. So you cannot just include the 0th element. So basically the thing is, you cannot just have partitions which are contiguous in this range. You can have partitions like this belongs to one part and these two belongs to another, right? Okay, so due to lack of time, I think so does anyone have any other suggestion? Okay, so turns out that yes, you can say yes every time x plus y is a factor of n times n plus 1 by 2. So now, how you can do this? Well, so you just need to find this sum of x k. So you need to sum of the elements in the subset is equal to x times k. Okay, so for simplicity, you can call x times k equal to z. Now observe one thing. Well, what is the range of z? Z can be from 1 to n into n plus 1 by 2. Correct. Z is a factor of this number, so it has to lie between 1 and this number. Great. Is that clear?
Yes.
Okay.
The upper bound will not be reached, I guess.
Yes. Yeah. Fair enough. Because y has to be 1. Okay. Now the thing is, we want a subset such that the subset sum is equal to z. Now tell me one thing. What happens if this is the case? How can you get a subset? Anyone?
Z should be Z should itself be the subset. I mean, the
Yeah, so
only
you
limit.
can just make this subset, I guess, right? 1 through up to n except z. Right. That's straightforward. Now, what about this thing? So if n is z is between this n plus n minus 1. So what you can do is basically take n and z minus n, right? sorry, n minus in one subset, and the other subset would have sorry, z minus n. Yeah, I was correct the first time. So z minus n is in the range 1 to n minus 1, right? Everyone agrees with this?
Yeah.
Okay. Now I think you can see where this is going. So if this is the case, then what do? You take n minus 1 and basically z minus n minus 1. Correct. And since z follows this particular set of inequalities, then z minus n minus 1 would be in the range 1 to n minus 2, right? So you can do this, and similarly you can basically extend this to any number of terms. So n minus 1 plus, let's say, n minus let's say I is less than z is less than equal to n plus n minus 1 plus n minus, okay, so just put this over here. Okay. Yeah. So in this case, you will just add all the integers n minus 1 to n minus I, and then the whatever remaining value you have. Okay. So you can basically break this down into ranges and then solve each range separately. So I hope this is clear, right? So why it should always be yes? So for any z in this range, you can break it down in one of these ranges, and you can have a corresponding construction to get the particular sum as z. Any questions? Okay, I hope it's clear. Well, so basically what we are doing is okay, so basically if z is greater than n, then we are definitely taking n. If z is greater than n, and then after taking that, if z is still greater than n minus 1, then we are taking n minus 1. So if z is greater than n, and after taking that z is greater than n minus 1, then even after taking that n minus 1 to your partition, then it's greater than n minus 2, and blah 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 up to n minus I. You have all of them to be greater than z, the sum of all of them to be greater than z, then you're taking out, right? So this basically means this basically means that you need to do something like whenever z is greater than the last seen value, then take it. Okay, so algorithmically, how would it look like? So something like you have some counter from so let's just for I from n to 1. Let's call this iterative. If z is greater than or equal to v, then you take this v in your subset and assign z to this value. Just subtract v B from Z. So this is your node item. So is everyone clear about this algorithm? So it's not very straightforward as in how this algorithm is derived from this particular proof, but yeah, I think it's pretty straightforward. But yeah, so it's not very rigorous. I think you can try to rigorously prove it on your own. Okay, so is there any doubt regarding whatever we have discussed till now? Okay, I hope I didn't put everyone to sleep. Anyway, let's just move on to the next. This is a small topic that we had. So this is called the rearrangement inequality. So, okay, so by raise of hands, does anyone know about rearrangement inequality? Okay, so I'll put this in real quick. Okay, so basically the rearrangement inequality says that if you have two sequences x and y such that they are non-decreasing and both have the same size, let's call them small n and y1. Then this particular set of inequalities hold true. So if you take the dot product of these two sequences as they are, this would be greater than the dot product taken with this sequence with any permutation of this sequence. So I'll just call the permutation phi of 1 x2 y phi of 2 phi of 5. And this value in turn is greater than or equal to the dot product with the reversed sequence. So x1 yn plus x2 yn minus 1 dot 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 plus xn times y1. Okay, so I should write this that phi is basically a permutation. Of 1. So basically it can mean anything like phi of 1 equal to 3, phi of 3 equal phi of 2 equals 1, phi of 3 equals 3, phi of 4 equals 5, phi of 5 equals 4. Yes. Okay, so 2, 1, 3, 5, 4 is a permutation of 1, 2, 3, 4, 5. Well, does everyone understand the statement of this inequality or this particular theorem? So I haven't proven this yet, but this is the claim that this value is greater than equal to this value is greater than equal to this value. The reason this is very important in comparative programming is that most of the greedy algorithms, not most of them, like 30 to 40% of the problems in greedy algorithms section can be solved using this rearrangement inequality. So I hope everyone is fine with this problem, with this statement of this theorem. Okay, so let's just go over a brief.
Can you once explain that y of pi on what is that?
Okay, so let's just give you an example. So if n is 3, let's choose another color. If n equal to 3, so x1, y. So for n equal to, let's make it 4. Can you just tell me a permutation of 1 to 4? Any permutation that you want.
3,
This
2,
would
1,
be
4.
3, 2, 1, 4. Okay. So I'm just calling this pi of 1, this pi of 2, this pi of 3, this pi of 4.
Yeah, I understood.
So basically this means that x1 y1 plus x2 y2 plus x3 y3 plus x4 y4 would be greater than equal to x1 y3 plus x2 y2 plus x3 y1 plus x4 y4. And for any other permutation, this thing would hold true, given that these two are both non-decreasing subspaces. And the minimum of these will occur when the permutation is the reverse permutation of the sequence of i's. Okay, so I think we can have a brief proof of this theorem. So I'll just prove this part. I think you can prove this part on your own. Okay, so how do you prove something like this will be greater than equal to any possibility, any permutation that is possible? Well, you assume that there is some other permutation of integers from 1 to n such that this value is optimal. So assume for some pi, so it can be something like 3214 or something like that. For some pi, this value. Okay, I'll just write it in the summation symbol like this. Sum over I from 1 to n xi y of pi I is maximum. Now, since you assume that this particular permutation is not the identity permutation, so there will be some I such that pi of I is not equal to I, right? There exists I such that pi of I is not equal to I. Well, out of all those i's, just take the minimum. Okay. So, for example, if you have pi as 1, 2, 3, 6, 4, 5, 7. So this is pi of 1, this is pi of 2, this is pi of 3, this is pi of 4. So this particular value pi of 4 is not equal to the numerical value 4. So you consider I equal to 4. Okay. So for any permutation that is not exactly the identity permutation, this must hold true. And assume that this is the first occurrence of such a value such that the permutation is not equal to the actual value that was there. That means for all, let's say, j less than, I don't want to use j. For all I prime less than I, pi of I prime is equal to I prime, right? Otherwise, you would have chosen I prime to be the minimum I. This part is clear, right? Well, now you just have a look into this value. So just assume that this value is j, which is not equal to I. And since all other I primes are taken here by some other values in the permutation, you can safely assume that j would be greater than I. So you remember the partition that I was talking about, something like 4, 5, 7. So you observe that since 1, 2, and 3 are taken over here, and if this value is not equal to 4, this value has to be greater than, strictly greater than 4. So I'm just calling this 6 to be j and 4 to be I, because this thing occurs at the 4th index and the value over here is 6. Now what you can further do is, since this is a permutation of 1 to n, j is a valid number between, so j is an integer between 1 to n, and hence a valid argument to the pi function. So you can actually talk about the pi of j and what it would be. So just assume that if pi of j is key. Okay. Now what does this mean? This means that your sum over here has two terms like so you have something like xi y pi I, so which is basically xi yj, and over here you have something like xjyk. Correct. Okay. Well, I think I did a particular mistake over here. Oh, okay, yeah. So never mind. Sorry. So instead of taking pi of j is okay, just forget about k, whatever I talked about k. Now just consider this I. So this I does happen somewhere later on in this sequence, correct? So if this particular value is not I, everything before that is same as the index that it is placed in. That means the value I occurs as a functional value somewhere after index I, correct? So you can have something like another index k such that pi of k is equal to I. And since this condition holds true, all the indices before I have something different than I. So in particular, they have something strictly less than I, but they are different from I, and hence k must be greater than I as well. Okay. Now this before that, after that, and then it has something like xk y of yk. Correct. Is this clear up to now? Hello? Okay, I think it might get a bit confusing. But well, the thing is, if you can swap these two values, you can basically check that the functional value will get even larger. So if you just, instead of writing pi of I equal to j and pi of k equal to I, if you could have swapped these two values, so if pi of I was I and if pi of k was j, then the resulting sum would have been better. So I'll leave this particular part of the proof as an exercise to you. And I think this part might be a bit confusing. So there is a good blog on this. Well, there's a good write-up on this in brilliant.org, so you can just search that if you're confused. Okay, so the proof is not that important, but I hope everyone is fine with the statement, right? Is there any difficulty in the statement? Okay. Okay, I hope the statement is clear.
Can you just go back? Means that last that x1 greater than equals x1 yn means how to prove it? Means I'm just asking you.
This part.
Yes, yes.
Okay, the easiest thing you can do is if you have proved this part, then you can take another sequence zi, which is equal to yn minus yi. Okay. So you will have something like Zn less than equal to Z n minus 1, and then you basically apply this inequality on this two sequences to get this part of the inequality. But
Okay, means I proved the first part using that only. Like I choose I less than j means those are two index, and I less than j. So xj minus xi is greater than 0, and yj minus yi is greater than 0. So I now multiply it. So
exactly,
that
exactly.
that should be
That
the
is the exact way you complete this proof. Yes, yes.
okay.
Okay, yeah, that's very good. Yeah, and of course you can come up with a similar reasoning for this part as well. So you assume the first point where pi of I is not equal to n minus I, and then just try to
Yes,
swap
yes,
those.
yes. Like I can make the j equals n, means index j equals n. I think xn minus x1 is greater than xn minus x2. I think.
Yeah,
I'll
yeah,
try it.
exactly, exactly. Yeah. Okay, uh, so if anyone is willing to see the complete proof or is confused regarding just entire proof itself, they can just check out the website brilliant.org, and it has, so basically searching rearrangement inequality in Google will land you up on that page itself. Okay, so what I'm more interested is to discuss this problem, the biggest restaurant. So this is a problem from November book of 2019 from Coach. So the problem is pretty simple. So you are given n coordinates x1, x2, x3, xn, such that they are strictly increasing xn, and the constraints are something like this is maybe 2 into 10 to the 9 or something like that. Basically, the point is they are large. I think they start before 0. x1, x2, xn is equal to 10 to the 9 or 2 into 10 to the 9. And you are given a set of poles. So you are given a set of n poles, and the ith pole has a height of hi. Now, what you can do is you can place this n poles on these locations. So you can place this poles in these locations in any order you want. So this can be h3, h1, h2, h4, something like this. So as you might already know that this will be a permutation and you'll be using rearrangement inequality, but it's not that clear till now. Okay, so I'll just complete the problem. Now, after this placement of these n poles, you want to maximize the area of this particular polygon. So you join these heads, and then so there are holes over here as well, and then you end up over here. So the entire polygon that you get, you want to maximize its area. So is the problem clear? You are given n coordinates, you want to place n poles in these coordinates, and you want to draw this particular polygon, and you want to maximize the area of this particular polygon. Any questions regarding the problem statement? Okay, so I'll assume that the problem statement is clear. So these particular heights are given to you. So h1, h2, hn, and these might also be in the same range. Well, this particular sequence need not be increasing as you are allowed to permute this. Okay. Okay, so I hope the problem statement is clear. Now, any possible approaches, any suggestions that you might have? Can anyone suggest anything? Okay, so I'll just give you guys a little push. Can you calculate the area of this rectangle for some permutation? So just assume that you have some permutation y1, y2, yn, which is basically a permutation of h1, h2, hn. And the first pole is y1, the second pole is y2, the third pole is y3, and the nth pole is yn. What is the area of this polygon?
We can find the area of the small trapeziums.
Exactly, and that would be. So what is the area of the first trapezium?
Half into x2 minus
x2
x1
minus x1
multiplied by y1 plus y2.
Okay, so since this half is here, let's just talk about 2 times the entire area. Okay, so that won't be a problem, right? So if you want to maximize the area, it's same as maximizing twice the area, right? So let's just get rid of this half. Okay. So let's just call 2 delta equal to this plus x3 minus x2, correct? y2 plus y3. xn minus 1 plus, I think I should write it over here, xn minus 1 y yn plus yn minus 1. Is this part clear? Is there a problem with this part? Anyone? Okay. So what can you write regarding this? So you can actually break this out. So if you take y1 separately, if you take y2 separately, if you take y3 separately, so what would you get? x2 minus x1 times y1 plus, so x3 minus x2 plus x2 minus x1. So it's x3 minus x1 into y2, right? Plus, so the next term would be x4 minus x3 y3 plus y4. So as you can see, x4 minus x3 plus x3 minus x2. So this will be x4 minus x2 times y3. Correct. So this will go on, and we will have something like xn minus 2 minus xn times yn minus 1 plus, now for the last term you don't have anything after that, right? So for yn it should be just this part. The same way for y1 is just x2 minus x1, not something like x2 minus x0, since you don't have something like x0. So it would just be xn minus xn minus 1 times yn. So is this part clear? So I've just broken down this y's and rewritten this entire equation. Is this fine? Anyone? I'm not getting any response. Okay, I hope.
Yeah, fine.
Okay, yeah.
On that, in that green line that you have wrote, the last term will be yn plus yn plus 1 or n minus 1.
Sorry?
Last term yn plus n minus 1, it would be or n plus 1. In this green line means with that.
This one, right?
Yeah. That highlighted one.
Okay,
Yes.
so it's of the last trapezium, right? So this is xn minus 1. This is yn minus 1. This is yn.
Okay. Fine.
So this, I think this is correct, right?
Mhm.
Okay. So can I move on? Okay, so I guess I can move on to the next part. Okay, now you remember this thing I assume. So y1, y2, and yn is a permutation of h, the array h. So basically x2 minus x1 is y1 plus x3 minus x times y2 plus whatever this is. So this is basically a dot product of some other sequence with a permutation of hi. Right. Now, can anyone suggest something?
Yeah, so we can just make a separate array for these coefficient, like x2 minus x1 should be an element, and then x3 minus x1 should be an element, and so on. So that we have that array, and we can just sort the array of the h's, and then take the dot product of these, and then take the sum. That's the correct answer.
So this should be minus 2. And then the last term and the first term are special. So I'm just writing them down separately. And
We can
then
just sort this one. No, you have to sort this one and sort that h array. Then need to take the dot.
Sort this array. Sort h. And that would give you the maximum value. Why?
Yeah.
Because basically after sorting this, if you get something like x3 minus x1, x4 minus x3, x2, x2 minus x1, xn minus 1, and then you pair this up with the sorted version. So I'll just call them h prime 1, h prime 2, h prime 3. So since you have sorted these two arrays, you will have the perfect setting that you had in the rearrangement inequality, and then you can basically prove that any other dot product of any other permutation would give you a worse answer. So the final answer would be this dot product, and maybe you need to take care of this times 2. So yes, that's the complete solution. Sort this, sort h, and then take the dot product. So this is a harder example on rearrangement inequality because of this. The more common way of using rearrangement inequalities is when one of these sequences are the standard sequence from 1 to n. So basically xi is equal to I. So this is a much more common example. And you're given some yi's, and you have to do something such that y1 times 1 plus y2 times 2. So something like y1 plus 2 into y2 plus 3 into y3 plus dot dot and into yn is maximized or minimized or something like that. And then the way you would do this is just by sorting this. Okay, so I've mentioned about these kinds of problems in particular portion over here. Okay, so I think we are running out of time. Let's just go on to the next problem then. Okay, so the next problem is taken from this forces round 782, problem C, I guess. Yes, problem C. So it's called the line in empire. So over here you are given some points on the x-axis, so 0, x1, x2, xn. So this condition holds x1 less than x2 less than xn, and this is less than 0. And there is an emperor on this point 0, and this point 0 is the capital for this emperor's empire. Now, what this emperor can do is it can conquer any city from its capital, and to do so, he needs to pay a cost of. So, if his capital is at C1 and he wants to shift his capital, he wants to conquer some region at C2, then he needs to pay a cost of A times the modulus, the absolute value of C1, C2 minus C1. Okay. And the second thing that the emperor can do is, if his current capital is at C1 and he has conquered some portion on this numbered line at coordinate C2, then he can move his capital to C2 by paying a cost of B times the absolute value of C1 minus C2 minus C1. Now the problem is you need to conquer all these values. So you need to conquer x1, you need to conquer x2 up to xn, and you need to pay the minimum amount of cost for this. Okay, so any suggestions or guesses?
Could you explain the problem once again? Like just the C1, two parts. Can you explain?
So there is something. So there's a number line, and there is something called the capital of the empire. So the emperor sits on this capital. So if this is C1, and there is some unconquered land on this number line at coordinate C2. This is 0, this is C1, this is C2. Then he can conquer this portion, this particular point. So it's not a portion, this particular point, by paying this cost, A times C2 minus C1. And by conquering, to mean that this particular point now belongs in the empire of this emperor. But the emperor still has its capital at C1. The capital does not move. Now the emperor also has this particular privilege of moving the capital to an already conquered land. So if there was some other conquered land, okay, let's just say this C3 was already conquered, and then the emperor wanted to shift this capital from C1 to C3. I'm bad at drawing arrows. Okay. Yeah, so from C1 to C3, then he needs to pay this amount of cost. So this will be C3 over here. So if the emperor wants to move from C1 to C3, where C3 is already conquered previously, then he has to pay this cost of C3 minus C1 times B. Is a problem here? And yes, you need to conquer everything, but you are given no restriction where the capital should be. The capital can be anywhere at the end of conquering everything or during the process. Okay, so I think we are running out of time. I'll just reveal the solution, I guess. So the greedy choice that we need to make is you can actually okay. So at the end of the entire operation, what would your number line look like? So your number line would look like conquered. So 0 was initially conquered and kept, and the capital. So conquered, and the capital at some particular position and conquered. Great. So 0, x1, x2, xn, where the capital is on some xi. Correct. Obviously, you don't want to conquer and place your capital over some other place which is not a given coordinate. Okay, so I'll just leave that proof to you. Anyway, Now the cost of moving from here to here, so the cost of moving the capital from here to here is same regardless of the path you choose. So, well, if you chose some path that goes here and then comes over here, then obviously it would be greater, or some path that goes here and then comes over here, that would be greater. But if you had chosen a path that is always goes to the right, then the cost would always be b into xi minus 0, which is basically b into xi. This is the cost for moving the capital. And now there are costs for conquering a city from a country. Now this is the part where the greedy choice comes. So whenever you are moving a capital to a particular city, so let's say, so I'll just take some examples. So let's say this is x5, this is x6, this is x7. Okay. Now the scenario was this. So this was conquered, this was unconquered, this was unconquered, and this was conquered, and your capital. So let's say at some point of time you want to move your capital after conquering, obviously. So after conquering x6, you want to move your capital from x5 to x6. So what would you do? You can do two things, I guess. So you can conquer x6 from this particular point, and you can conquer x7 from this particular point, and then move the capital from x5 to x6. And the second thing that you can do is as soon as you conquer this position, you move the capital over here, and then you conquer this x7 from x6. So observe that this is way better, because over here, so in the first sequence, so you conquered x6, conquered x7, moved to x6, right? And in the second example, you conquered x6, moved to x6, and then conquered x7. So what is the cost over here for this particular set of operations? You conquered x6, so it's a into x6 minus x5, plus you conquered x7 from x5, so it's x6 minus x5, and then you move your capital to x6 from x5. And over here you have something like x6 minus x5 this should be x7, so you're conquering x7 from x5. So yeah, okay, coming back over here, it's x6 minus x5, then you're moving your capital to x6, which would basically mean x6 minus x5, but the coefficient would be b. And now your capital is at x6. This means that the cost of conquering x7 is x7 minus x6, not x7 minus x5. Now you check that this term is same as this term. This term is same as this term. But this particular term is greater in the previous set of moves than this particular one, because of the simple sequence that is given to us. That is, xi's are in strictly increasing order. So the greedy solution to this is basically moving from. So whenever you want to move your capital, you need to move it immediately after conquering. Now I'll not discuss the entire solution with this, but try using this particular property to come up with some solution that solves this problem. So this particular for this particular configuration where you know that the capital will be at xi, you know that whenever you move your capital, you move it immediately after conquering, and then you conquer everything from here. But this xi is not known yet. So what you can do is you can iterate over all xi and do some math to get this particular cost in constant time. So I'll leave that to you as we are currently running a bit. So we are currently past the end time. Well, I had another problem in mind that I wanted to cover, but okay. So small comment regarding this problem. This problem was authored by one of our members in Primar of Code and Code Forces round, Moina Ploy. So that's great. And let's call it a day then. So any questions regarding whatever we discussed?
Next class is also on greedy algorithms.
I was thinking no, but so I'll share this slides and then you can these problems. So there is like greedy algorithms is vast topics if you vast topic if you just want to get a problem. So it's basically a way of solving a problem, right? So there can be countless problems on this topic. So I think let's see what happens in the next class. Also, is there any pressure over here from previous semester? I mean, previous semester in this spring sem?
Yes.
Okay, can you tell me if recursion has been completed in your normal classes?
Yeah.
Okay, that's great. That's great. Okay, so in the next class we can have dynamic programming or something, right? Moina, are you here?
Yeah.
Yeah. So their recursion is done in PDS class. So I think we can have recursion and backtracking or dynamic programming or something like that in the next class, right?
Yeah, that we can do. I mean, backtracking, do we really need to teach backtracking?
And let you guys know.
Hmm?
Okay, so any other questions regarding what was covered? Any comments? Any suggestions that you would like to give? So someone was saying if the next class will also be in greedy. So like, do you want more greedy discussions?
Like you
problem-
said, the 40% of the questions are from the rearrangement formula. Now the remaining
50% is a like rough estimate, but yeah, the remaining part is basically making greedy choices
okay.
like taking consecutive elements, then taking the largest element that is greater than this. So in general, these are the things that you do. So there were a couple of incorrect greedy suggestions, but these two sometimes happen to work, right? So taking the minimum, taking the maximum, these heuristics are often important. Also, like I hope everyone is clear how to prove that a solution is that a greedy solution is optimal. So I think you can just search the internet for this, but the part I've done over here in the rearrangement inequality is essentially the way most of the greedy problems are proven to be correct. So basically, you assume that some other solution which is different from the solution that you obtained by a greedy algorithm is optimal, and then you make changes uh, in this particular solution, and then you see that the value you're getting is actually better than the value that so making a greedy choice is actually better than coming up with some other techniques, right? So over here for an example, the simple problem that we had for choosing three indices of the array. So here you argued that well, if some other solution exists, then we can just swap in an integer from the minimum 3 of these and then get a better answer. That's the way we do it. So I hope that part is clear.
Yes.
Okay. And so basically, most of the greedy tutorials on greedy algorithms would talk about the classical problems. So I've listed the a set of classical problems that I know. So you can basically go over this, and I've some problems from CodeChef, CodeForces, HackerRank, and etc. And some other resources that I have. So I'll share these guys, I guess. And I also wanted to talk about this problem aggressive cows, which is basically a binary search problem with a uh, greedy way of checking that a value is valid or not. So if you can open this problem and have a look at it, it would be great. But yeah, due to lack of time, we couldn't discuss it. You can even check it out. So yeah, so now my main question is like, if you want another greedy session, there can be another greedy session. So yeah.
So I want to ask one thing, that understanding greedy is basically more on practice, or we need to cover more theory on it?
There is not much theory in video algorithms. I couldn't think of anything other than a rearrangement inequality that establishes as a separate theory other than video algorithms. Video algorithms is basically where you make greedy choices. So that comes solely from practice.
Also, greedy algorithms require good data structures hold, like good grip on data structures, or is it okay if we don't have that much?
I would say the opposite. I would say the opposite. That greedy algorithms, like coming up with a greedy solution, uh, lets you avoid complicated data structures rather than using them. So you will learn about dynamic programming and maybe about. So you have learned about sets and SQLs. So sometime later you might come across some data structure known as segment tree or something like that. So oftentimes there is a solution that uh, you can have with the segment tree or some other data structures that is very lengthy in terms of lines of code. But by making a greedy observation, you can eliminate that data structure and just sort it and get optimal solution or something like that, right? So, am I making sense right over here?
Yes, yes.
Okay, so I hope your question is answered. Any other question? Or suggestion?
Like in future, could you take some sessions on data structures and like STL data structures along with other data structures also, including problems, not just explanation, problems also.
Okay, okay. So, what all data structures? So, do you have any suggestion on what data structures would be better to take?
I think so. You know it better, which will come more
Okay.
use div 2, div 3.
Okay, okay. So basically, the STL data structures is like mostly the entire exhaustive set of the data structures that we use in div 2, div 3 problems, I guess. Yeah, so yeah, we can share problems regarding the data structures, but okay, I guess we can have a session where we can explain solutions to problems using these STL data structures.
Yeah.
Okay, then.
Except stack and queues, which data structures are used? Like, in